I'm Samantha Irvin. I'm from Rose Creek, Minnesota. I go to school at Wartburg College. It's in Waverly, Iowa. And I spent my summer here at the Colorado School of Mines working for the physics department. And I worked on the mesoscale modeling of quantum yield in nanocrystalline devices. And what I did was we used a computer program called COMSOL Multiphysics, and I simulated a solar panel cell with silver, zinc oxide, and then silicon layers of p-type, I-type, n-type, with silicon quantum dots in it, and then with an ITO layer on top, and then an air layer, PML, perfect match layer for the optical models. And our goal was to find a device response for nanocrystalline as a function of the nanocrystalline dot size. And in order to do that, we wanted to find the optimal short circuit current using the size. This would be great because it could offer design guidance for nanocrystalline silicon and amorphous composites. And some of the things, nanocrystalline silicon properties are that it has a band gap of 1.1 eV versus amorphous silicon, its band gap is 1.7 eV, so they absorb different areas of light on the spectrum. They have different carrier mobilities. Nanocrystalline has a higher carrier mobility, while amorphous has a low carrier mobility. And then amorphous also has a low doping efficiency, whereas nanocrystalline has a high doping efficiency. So it worked really well to combine these two kinds to see what we can get out of the model with both of them. And what we did was that we put the nanocrystalline silicon quantum dots in our intrinsic region. It was an amorphous silicon intrinsic region, and we packed them at about 50%, and we kept that constant for this. And what I did was we had different modules set up with my model using COMSOL, and we ran the optical models in order to find what sort of scattering and absorption we get for different light. And we looked at it from 300 to 1,000 nanometers, because with the index of refractions that we had for a lot of the layers, those were just the range of light waves that worked the best. And so we shined light down from 300 to 1,000 nanometers, and then we stored what we got out of that and integrated it with the light spectrum model in order to find the absorption. And then we saved that in the model to use later on. And then we looked at one of the electrostatic modules. And what we did here was we used a zero current base case in order to find an initial guess for phi, our electric potential for the model. And we had to do this because it just worked a lot better if we were able to give the program a guess. So it was a lot closer in order to actually find phi itself later on. And then we ran the last electrostatic, and then we had two convection and diffusion modules, and those were in order to find the drift and diffusion of the charge carriers. And we ran those three together, and then we put in the scattering and absorption we got from running the optical models, as well as our zero current base case for the initial phi knot. And then we used that in order to find out what sort of short circuit current we got out. And that itself was hard enough to set up and get done. It took a lot of time. But by the time we got the model to run and to do all that for us, what we did was we changed the size of the dots in order to find what's the optimal quantum dot size for this. And Aaron Madden of MB Systems in Golden, Colorado, we had a meeting with him where we found out from him that they like to make the dots large, because the larger the dots, the better. So we were trying to show that, yes, the larger the dot is, the better current you get out, and so it would make a better model. And we ended up getting some interesting results. That's just about the most anybody said is, well, that's really interesting. They start increasing fairly steadily here, though, starting at a 13.5 nanometer semi-minor axis dot, so like 13.5 nanometers that way. And we only got up to 22.5 nanometers for our semi-minor axis, because just with the thickness of the I-type layer, that's just the largest size of dot we could get. Well, hopefully, if you were able to make a larger dot, you could see that it would still increase, and then show that, yes, the larger the quantum dot, the better. Some future work that can be done with this model is to make the thicker intrinsic layers so that, yes, you can see what sort of short circuit current you get then with a larger dot. Also, to put it in 3D, this is only a two-dimensional model, and so it's not really quite realistic, because the dots end up being acting more like rods. And so if we were able to put it in 3 dimensions, it would make it much more physical. And then another area would to see what is the optimal packing efficiency. We just used 50%. That was just what what I was told to use and what's been found to work, and so hopefully somebody can show like why 50% packing efficiency is the best, and you know, just which one works better. And that was my mama.